Okay, so from here, can we use the same idea in base 10 to have, a slightly different way of looking at 1?
Alright, so if we wrote 1 now in base 10, we could write it as 1. But then if we don't use the 1's digit, we have 0 point. And then in this case we have a little bit more choice because we have the 10th digit and the 100th digit. We can use up to 9 of them. Let's see, so if you use 9/10, you're still under 1, so we can subtract 9/10 away and be left with 1/10. And so, actually, I'll just write what the sum is. So we're summing 9/10. Using 9/100th still keeps you less than a 10th. We'd be left with 100th plus 9/1000ths. And so on. And then this would be how the sum would repeat. And so we'd be left with the sum 9/10ths plus 9/100ths plus 9/1000ths. Next term would be 9 over 10,000. So you take the previous term and just multiply by a 10th.
Okay.
Let's see, so we'd have to prove that this sum equals 1. I guess I can just erase.
Yeah.
So our sum, 9/10ths plus 9/100ths plus 9/1000ths plus, and so on. Now I can erase this. We can set it equal to x. And I guess we can also factor a 9 out of all the terms because the 9 will stay on the top for all the terms.
Okay.
So 1/10, 100th, and 9 times this. So let's see. Well, if we multiplied every term by 1/10 again, we'd get 9 times 1/100th plus 1/1000th plus 1/10,000th, and so on. And this equals x over 10.
Okay, really nice.
And so now we can subtract x over 10 away from x because these terms are going to line up. So every term in x over 10 corresponds to a term in x, and the same holds true for x, but we are left over with 1/10. So we have 9 times 1/10 equals 9x over 10.
Okay.
And so we can see that this becomes 9/10, and this becomes 9/10 times x. And so we can say that x equals 1.
Nice.
Cool.
Cool.
So yeah, this sort of shows using fractions, and similar to base 2, how 0.99999 equals 1.
Alright, so yeah, it's kind of a new way of looking at it. And starting to see that, yeah, maybe this is true.
Yeah.
Maybe it is. Okay. Good work this morning. Great job.